Hi, good day, and welcome to my first video on physics basics. This series of videos will be focusing on topics that every physics student needs to know in order to progress from easy questions to hard questions. So let's jump straight into it. The first topic I want to discuss today is something called gradient. Now, this is just going to be a brief introduction to gradient, and after we learn the basics, I'm going to show you how you can apply it to physics questions. However, if you are interested in learning the entire topic of gradient, the easy stuff and the hard stuff as well, please feel free to go on YouTube. In the search menu, just in the search bar, just type in I love lessons. Don't forget this S here. There are no spaces. Then put a space and the number 51. The first video that should pop up is a video explaining gradient and the equation of a straight line in detail. So I suggest that if you want to learn gradient in detail, go to this video. Alright, so let's get started. So I'm going to show you all how to find the gradient of a straight line. Here we have a graph with a y-axis, which is the vertical one, and a horizontal axis, better known as the x-axis. Very important that you remember the x is horizontal, the y is vertical. And here we have a red line on the graph. Now, I'm going to take 2 points on the graph, point A and point B. Let's assume that point A, its coordinates are 5 and 10. And the B point, let's assume that the coordinates are, let's call it 7 and 28. Right. So in order to find gradient, we need to utilize this formula. The formula is y2 minus y1 divided by x2 minus x1. When you have points on graphs, the first one is x and the second one is y. So for point A, x will be 5 and 10 will be y. Similarly for point B, the first point is 7 and the second point is 28, making this x and this y. Alright, now according to the gradient formula, it says y2 minus y1 and x2 minus x1. You notice the formula has smaller subscripts 2 and 1. So where does that come from? Well, remember that we have 2 points A and B. Choose any point first. It does not matter if you choose point A first or you choose point B first. But let's just choose A first. If we choose A first, everything in A will have the subscript 1. So he becomes x1 and he becomes y1. Everything in the first chosen point has the number 1. So if we choose A first, that means we have to choose B second, which means everyone in B will have the subscript 2. Right, remember, if we chose B first, everyone in B would have a 1 and everyone in A would have a 2. Either way, we are going to get the same answer. So let's calculate the gradient of this line. The gradient basically means how steep the line is. But anyway, let's calculate the gradient. According to the formula, there's a minus sign on the top and underneath. So how much is y2? Well, y2 is 28 minus y1 is 10 divided by x2. How much is x2? x2 is 7. We must put the minus sign. And x1 is 5. Right, so all we need to do is work out the top on our calculator, the underneath on our calculator, then divide our two answers. Alright, so let's, I think we need a calculator. 28 minus 10 is 18. 7 minus 5 is 2. And well, 18 divided by 2 is 9. So the gradient of this line is 9. Pretty simple example. I don't want to go too much, do too many examples on gradient because I already have a previous video explaining it in detail. But I want to point out a few things here. For gradient, at the end of the day, what we're really doing is taking the y values and dividing it by the x values. So basically, you can see it like this. Gradient, you're taking the y's and dividing it by the x values, right? So gradient is just basically the y's divided by the x's. Just to really simplify. Or remember, the y values, the y-axis is the vertical and the x-axis is the horizontal. So another way of looking at it is that you're already taking the vertical values, VR is just an abbreviation for vertical, and you're dividing them by the x values, which are horizontals. So that's another way of looking at it. Instead of using this formula, you're already taking the x and dividing it by the y's, or the verticals by the horizontals. So how can finding the gradient be useful in physics? Let's apply it to a real formula, theorem in physics. Anybody who is doing physics, like the first 3 months of physics, will definitely run into this topic. It's called Hooke's Law. And here we have the formula for Hooke's Law. So let me just explain. There are more than one ways of writing the formula. I just want to show you how they relate to each other. Hooke's Law is it's used for for springs. Let's say we have a ceiling, and on the ceiling you have a spring, right? And you all know that springs can stretch. If you release the tension, it will go back to its original length in most instances. So we have a spring, and attached to the spring we put a weight. Now obviously, if we put a weight on the spring, it will stretch the spring. The spring should get longer. When something gets longer, you can call it an extension. So in this little experiment here, we're going to be putting different weights on the spring, and the weight is going to be measured in newtons. Now you might not know this, but weight is not measured in kilograms. Weight is measured in newtons. And force is also measured in something called newtons, capital N for newtons, which means weight is a type of force. So as we add more and more force to the spring, the extension should get larger. And of course, there's a formula to relate the force and the extension, and this here is the formula. Well, let me point out this one first. I want to show you the relationship between this and this. Force is equal to K. I will explain what K is just now, multiplied by the extension. The K stands for, is basically the spring constant. And the value of the spring constant gives you an idea whether it's a very strong spring or a very weak spring. If the K value of a spring is large, that means it's going to be difficult to stretch it. It's a strong spring. If the K value is small, that means it's a weak spring, meaning that I can take the spring and easily stretch it or extend it. So finding the K value of a particular spring is a very common question that comes in the exam. And I'm going to show you how we can use gradient to figure out the K value. Now this formula and this formula is the same. Force is K multiplied, there's a secret multiplier in between here, multiplied by the extension. You can write this formula in the triangle form. Anytime you're trying to find one of the letters, you just block it. So if I'm trying to find F, I block F. So let me block the F here. If we block the F, we end up with K multiplied by E. So to find F, you take K and multiply by E. If we are trying to find the extension, well, we just block the extension, the letter E. Extension is equal to force divided by K. And that would make sense, because if we're trying to find E, and we have to make E the subject, we would have to throw across K, which is a multiplier. And when you throw across a multiply, it will go underneath, becoming a divide. And similarly, if you wanted to find K, the spring constant, you block K. K is F divided by E, and we see this is it can be applied to this formula as well. To find K, we would have to make K the subject and throw across E. Now E is a multiply, throw it across, you will get a divide, right? So this and this, the one underneath and the one on top, are basically different ways of writing the same equation. All right, so I'm going to show you a real question with actual values and whatnot involving this formula and this particular experiment, right? So I actually pre-printed a graph. I'm going to have to zoom into the graph. The graph is very, very small. So let me just erase a few things here, right? You can fast forward, right? All right. Let's leave this formula. I have a good feeling we're going to need this formula again. All right, so to zoom in, I bought a piece of equipment, the Zoominator 3000X. Let's hope it works fine. All right, so this is it here. All right. Hope you all can see it. The actual values are pretty small, but I'm going to summarize it later in the question. All right, so here we have an experiment, and what we did in the question, in the experiment, we applied a force to the spring, and the force created an extension. The extension is being measured in centimeters, and the force is measured in newtons. So what happened, we did it for a lot of values, and we plot the points. We didn't get a perfect straight line, so we drew a best fit line. And after we drew the best fit line, I took two values. Whenever you're taking values off a graph, try not to take values that were originally used to plot the graph. When you draw the straight line, you choose any 2 points on the line, 2 new points, and estimate the x value and the y value. And for the other point, the x value and the y value. So using this graph now, we're going to try to figure out the k value of the graph. So these are my 2 points. I'm going to call the first one A, and I'm going to call the second one B. And what I did, I estimated the values. So you can see that x here is 10, and the y value is approximately 8. For the B point, the x value is 40, and the y value is 17. Right, so I'm going to choose point A first, x1 and y1, and B will be x2 and y2. All right, so I'm going to go back and put this graph on the whiteboard once again. All right, so I hope you can still see it clearly. All right, so how can we use gradient to figure out the k value of the spring's constant? Let's analyze this formula. Let me put down the formula for k. To calculate k, we have to take force and divide it by extension. So let me write it back so you can see k alone. To find k, you have to take the force and divide it by the extension. Right, now you will notice something. Remember, to find gradient, you're basically taking the y values and dividing it by the x values. You will notice the force is on which axis? The y-axis, and the extension is on the x-axis. The force is on the y-axis, and the extension is conveniently laid out on the x-axis. So that means if I were to find the gradient of this graph, I am taking the y values, better known as the f values, and dividing it by the x values, better known as the extension values. So by finding the gradient of this graph, I am effectively finding the spring's constant. So let's finish off this question, and I'll use the correct units also. So y2 is 17 minus y1 is 8, x2 is 40 minus x1, which is 10. So 17, let's double check my working, 17 minus 8 and 40 minus 10. Let's see what that gives us. I shouldn't be using a calculator for this, but 17 minus 8 is 9 and 40 minus 10 is 30. Let's just put it to 2 decimal places. 9 divided by 30, I believe. 9 divided by 30 is, oh, I got a nice answer, 0.3. But let's use the correct units. Remember, force is measured in newtons, and in this experiment, the extension was being measured in centimeters. So we are taking newtons and dividing it by centimeters. So the units will be newtons per centimeter. And that there is the spring constant for this particular string. Right? I think this is a pretty weak spring, because for every 0.3 newtons, it will extend by 1 centimeter. So I don't think that's a very strong spring. A baby or a child could probably stretch that string with ease. All right. So let's try another question with a trick in it. All right. So let's get to our second example. Here's another formula that you will meet up in physics. This formula helps us to calculate the density of a material. Now, just in case you don't know what density is, to give you an easy explanation, matter is made up of smaller particles, atoms, and molecules. Density gives you an idea of how closely packed these atoms or molecules are. So to calculate density, I've written the formula 2 different ways, like you previously saw for Hooke's law. Mass is equal to density multiplied by volume. And of course, if you block the m, once more, if you block the m, mass is equal to density multiplied by volume. It's the same formula. And once again, to find any letter, you block that particular letter. For example, volume is what? Mass divided by density. So you're going to realize from most of my videos, when I present a formula, I'm going to present it 2 ways, because in some textbooks they write it like this, and of course in some textbooks they might write it like this. I just want to get you familiar with both formats. Alright, so let's assume that we did an experiment, and in the experiment let me zoom in once again using the zoominator. Oh my. Alright, here we go. So we did an experiment where we had different masses and we had different volumes. And in the experiment, we collected the information and we plot the points. And once again, we did not get a perfect straight line, so we drew a best fit line. And when we did this, you'll notice that the volume is on the y-axis and the mass is on the x-axis. That's going to be very important in a little while. So what we're going to do, I'm going to calculate the gradient of this line, and I'm going to show you what the gradient of this line represents. So once again, to calculate the gradient, I did not choose 2 of my original plotted values. After I drew the best fit line, I took 2 brand new points. I'm going to call this point A, the first one, and the second one point B. And here's the x value and the y value, the x value and the y value. Right? Identifying the x and y value should be easy at this point in time. All right, so let me put back this graph paper to a more convenient location. All right. So let's calculate the gradient of this line and let's see what it could represent. Now this is going to be a trick question, so be prepared to see something a little bit different at the end of the video. So for point A, this is x1 and this is y1, and for B, this will be x2 and this will be y2. You see how I physically write in x1 and y1, x2 and y2? I would encourage any student to do it like that. Don't imagine x1 and y1 and x2 and y2. It's really easy to mix them up when you're imagining it and you're under pressure in the exam. So let's calculate the gradient here. Y2 is 37 minus y1, which is 17. X2 is 100 minus, and x1 is 40. Let's work this out. Let's see what we get. 37, not too sure why I'm using a calculator. 37 minus 17 gave us 20, and 100 minus 40 is 60. So that means that the gradient of this line is 1/3. Great. What does this 1/3 mean, right? Well, let's look at this. According to this graph, right, what is being measured on the y-axis? Well, volume is being measured on the y-axis. I'll put in a video. Well, I can put it here. The volume is going on top, and the underneath, the x-axis has the mass. So what we are really doing is taking the volume and dividing it by the mass. But let's go back to this formula. Density is mass divided by volume. So let's make D the subject here. If we were to make D the subject, throw across the multiply and divide it by the volume. So if I wanted to know the density, I would have to take the mass and divide it by the volume. But which axis is the mass on? The mass is actually on the x-axis. And which axis is the volume on? That's the y-axis. But when we found the gradient, right, we were doing the opposite. Remember, the volume is actually on the y and the mass is on the x. So that means to calculate the density, it's actually the opposite of the gradient. So if I wanted to find the density, I would need to flip this value. Flip this value. The x needs to be on top and the y needs to be underneath to get the density. So that means the density is actually not 1/3. It's actually 3 on 1. You have to flip it. The 3 goes on top and the 1 goes underneath. And 3 divided by 1 is 3. And to get the units correct, remember mass is measured in kilograms and volume is being measured in meters cubed. So that means my density is kilograms per meter cubed. The point of this question is that sometimes when you find the gradient, it doesn't give you something important. Sometimes you need to flip it in order to get the value of something else. So in every question that I'm going to be doing today, ask yourself at some point in the question, is he going to flip the gradient value or is he not going to flip the gradient value? Alright? So that's one of the main things I want to tackle in this entire video. And I'm going to be using a ton of examples. Alright? So let's get another example rolling. Alright, so welcome to my next example on finding gradients and utilizing it in physics. Alright, here's another formula that you're sure to bounce up very, very soon in physics if you started to study it. It's called Snells Law. Now let me explain, I know you probably don't, the first time you've seen it, so I just want to give you the basics. What Snell's law is used for, it's used to calculate refraction angles. So let me give you a very simple scenario here. On the board, you will see an air glass boundary, and we have a ray of light trying to move from air into glass. Now, from personal experience, I'm sure that you all have seen like a straw in a glass, and when you look at the straw inside the glass, it looks twisted. That's because of something called refraction. So whenever light tries to go from one substance, in this case air, and tries to enter another substance, the light usually bends. And there's a unit that allows you to kind of figure out how much the light will bend. That value is called N. Now the official name for N is something called the refractive index. By looking at the value of the refractive index, you can get an idea of how much the light will bend, and they measure the bending of light using angles. For example, this light might be coming in at, probably this looks around 60 degrees, but when it enters the glass, you notice the angle changes. It might be, in this case here, this angle looks a little bit smaller. It could be 45 degrees, 30 degrees, I'm not too sure. I don't really have a protractor on me. But to calculate the refractive index, you have to take the angle sine, well, the angle I. This is called the incident, the angle of incidence, sorry. The incident angle, I should have put that in before, and the angle where it gets twisted at, right, is called the, well, refracted angle, or angle of refraction. Alright, now remember, this is degrees, so it might be 60 degrees, 50 degrees. So what we're going to do, we're going to do an experiment. We're going to aim the light at different angles. So I will change, and of course if the angle of incident changes, you can expect the angle of refraction to also change, right? But to keep in mind, the refractive index is sine of the angle of incidence divided by sine of the angle of refraction. Right, now at the end of the question, well, during the question, you're going to have to, this question has something to do with gradient. You are going to have to make the decision at some point, as if we have to calculate the gradient and take it as it is, or would we have to flip it in order to find the refractive index, right? So let's see if you really understand what's going on here. All right, so let's zoom in again. Let's see if you have space on this corner here, and make sure it fits on the screen. Let me show you the values that we use for this particular experiment. Here we have the angle of incidence. That's the incoming angle. And for every angle of incidence, we recorded our angle of refraction. So we changed the angle of incidence and we got different angles of refraction. This is a standard experiment that you will have to do in school at some point if you're doing physics. Now, for each angle of incidence, we sine its value. So if you type in sine 10, you will get this. If you type in sine 6, you will get 0.11. So for each one of these, we sine the values and we rounded it off to 2 decimal places. And for each angle of refraction, we signed it on our calculator. And, well, just in case you don't know the sine buttons, and I'm going to show you how to use it quickly. All right, hopefully you can see there. Let's try this one, sine 10. You just press sine, enter 10. 10 is the angle. Press equal, and you notice we got 0.17. So I just rounded off each value. So in case you don't know how to use the sine function. Right. So what we're going to do, we're going to take the sine I values and plot it on a graph, and the same thing with the sine R values. And this here is the graph that we got. Now I followed the examiner instructions exactly as he told me to do it. He said to plot the graph of sine R versus sine I. Whenever they use the word versus, the first one is always the y-axis, and the second one after the word versus is the x-axis. So that means I was required to put sine R on the y-axis and the values of sine I on the x-axis. And we plot the graph. We did not get a perfect straight line, so we drew a best fit line. And once again, I took my own 2 new points on the graph. This is point A, and this here will be point B. And what I am going to do, I'm going to find the gradient of this graph, right? So I use these values here to plot this graph here. All right, we'll put this back in a convenient location. All right, so let's calculate the gradient of this line. All right, to calculate the gradient of this line, well, point A, x1, y1, x2, and y2. Let's calculate it. y2 is 0.54 minus, how much is y1? 0.2. x2 is 0.8 minus x1, which is 0.3. Let's double check my work in here. Right, everything seems correct. So let's work this out. I think I will need my calculator this time. Alright, let's see. 0.54 minus 0.2, that's 0.34. And well, 0.8 minus 0.3 should be 0.5. So if we were to divide this, 0.34 divided by 0.5, I got 0.68. Now, let's figure out if we needed to flip the value. To calculate the refractive index, which is the aim of this question, we have to take sine I, and divide it by sine R. Let's see what we have on the graph paper. Well, it seems that we put sine R on the y-axis. So that means this ended up on the y-axis. And sine I, ended up on the x-axis. But to calculate gradient, we took the y, we need to take the y's and divided it by the x. So this value, the gradient we just calculated, does not match up to the formula. In fact, to calculate the refractive index, we needed to do the opposite, which means this 0.68, we need to flip it in order to get the refractive index. Alright? If I had put sine I on the x and sine R on the, if I had put sine I on the y and sine R on the x, like they traded places, then if I calculated the gradient, then that would be the refractive index and there would be no need to flip it. So to calculate the refractive index, I need to flip it. So how do we flip a decimal? 0.68 is the same thing as 0.68 on 1. If we flip it, we will get 1 divided by 0.68 and 0.6, well, that's 1 divided by 0.68 is 1.47. So my refractive index for this particular experiment is 1.47. And it's very important to note that a refractive index does not have any units. Unlike the other two previous examples, remember the K, the spring constant, had a unit, and then density also had a unit. Refractive index, and your teacher will mention it, does not have any units. So the final answer for the examiner is 1.47. Right, let's do another example. Alright, so let's get another example rolling. Here we have a pendulum. Now, I think everybody has a good idea what a pendulum is. You take a string, you put a weight to one end, you move it to the side, and of course if you release it, it goes back and forth. Now, there's a formula that relates the length of the string, right? The string must have a length, and the time it takes to go back and forth. Now, if I pull the pendulum to point A and I release it, and time how long it takes to go back at point A, that time is represented by capital T, better known as your periodic time. And there's a formula that relates L and T, because if you change the length of the string, the time it takes to go back and forth will change to suit. And here is the formula. T is equal to 2 pi, don't let the pi frighten you, square root of the length of the string divided by G. G stands for gravity. The average value of gravity on Earth is roughly 9.8. In this experiment, we can actually do this experiment to calculate the value of gravity on Earth. And this is exactly what we're going to be doing in today's question. So, using graphs, let's say that in school, you had to do this experiment. So you got a pendulum, you measure different lengths of the string, and you time how long it takes to go back and forth. Okay, better known as a periodic time. And from that experiment, you're going to plot a graph for different values of length and calculate the value of gravity. Now I'm going to skip some steps in this, right? We're going to make some assumptions. So I want to show you how we can alter this formula. First of all, using your math skills, we have 2 pi here. This square root sign, you notice it's kind of big. It goes above the L and the G at the same time. What this basically means is that the square root sign belongs to L and it also belongs to G at the same point in time. So we can rewrite this formula like this. The square root of L divided by the square root of G. So what I did, I gave each of them their own square root sign. This and this is mathematically correct. What I am going to do now, see if you can visualize this. If I have 5 multiplied by 4 over 3, did you know that you can write this like this? 5, and the 3 could slide underneath the 5 if it wishes and leave the 4 separately. Right? So all I did was move the 3 underneath the 5. This and this is the same thing in math. You will get the same exact answer. I'm going to do the same exact thing here. You see the square root of G, pretend it's the 3. And I'm going to slide it underneath the 2 pi. So this here, I'm going to slide it underneath here instead. Alright? So what we have here is the square root of L separately. So I'm just going to slide it around. So of course, there's a secret multiply in between here. So multiply by the square root of L. So I kind of just pushed it aside a little bit. So when we did the experiment, remember, we were changing the values of L. And of course, timing how long it would take to go back and forth. So let's assume that we did the experiment and the examiner or your teacher told you that he wants you to plot T on the y-axis, and he wants you not to put L, but the square root of L on the x-axis. So, for example, if the length of the string was 25, the square root of 25 would be 5, and that is the value you would put on the x-axis. And let's assume that when we drew the line, we got something like this. We got a straight line. Well, we didn't get a perfect straight line. We got different dots, and we just drew a best fit line to suit the scenario. So let's see what we have here. T was required to go on our y-axis, and square root of L was required to go on our x-axis. Right. So remember, we're trying to calculate the value of gravity on Earth, which is roughly around 9.8. Let's transpose this formula. Let's make this funny looking thing here the subject. Throw across the multiply and you will get what? A divide. So that means if we transpose, over here we have T, and we throw across the multiply to get a divide. So this whole thing is a secret multiply. When it goes on the other side, we get a divide. So remember, T is going on which axis? The y-axis. And the square root of L is going on our x-axis. Alright? So let's find the gradient. So that means if we were to find the gradient of this line, remember this is the correct thing we have here for gradient, y divided by x. So I don't think there's any tricks here. If we were to find the gradient of this line, it would be equal to 2 pi divided by the square root of g. So this here is equal to the gradient of the graph. So let's say that we took 2 values of the graph and have x1 and y1, and we use the formula. And when we use the formula, the gradient of this graph happens to be 1.89. So after we use the formula, we got 1.89. So I skipped some steps and whatnot, right? But the point is, the gradient of this line is 1.89. How can we use this 1.89 to calculate the gravity on Earth? But remember, we said that when we found the gradient, it would be equal to 2 pi on the square root of g. So that means this 1.89 is equal to 2 pi on the square root of g. All we need to do now, right, let's erase this now, right, is use our algebra skills to solve for g. So I'm going to cross multiply. 1.89 is the same thing as 1.89 divided by 1. So let's cross multiply. I'm going to run out of space here, so go backwards here. Let's multiply this first. 1.89 multiplied by the square root of g is just 1.89 multiplied by the square root of g is equal to, we're going to cross multiply this diagonal now, 2 pi multiplied by 1 is just 2 pi. Let's solve for g. Between here and here is a multiply. Throw across the multiply, you will get a divide. Let's work this out on our calculator. Do not let the pi get to you. Pi, in case you didn't know, pi is just the same thing. Well, it's approximately 3.142. So all I'm going to do on my calculator is take 2, multiply by the value of pi, which is 3.142, and then divide that answer by 1.89. 2 multiplied by 3.142 divided by 1.89. And when I do that, I get 3.32. But I'm trying to solve for g. What we found here is the square root of g. So that means I'm going to have to throw across the square root. Now when you throw across something in maths, you get the opposite. So the opposite of square root is squared. So this 3.32, when I throw across the square root, I'll be forced to square it. And let's see that. 3.32 squared is approximately 11.02. Now remember, this is an experiment we did. Now when you're doing the experiment, there are always going to be slight errors. Like you might not have timed it properly, you might have measured the length a little bit off. So for this particular experiment, I got the gravity on Earth to be 11.02. The real value is supposed to be, like I said, 9.81 if I'm not mistaken. So according to the information, according to the data that I put into the graph and when I did the experiment, I was slightly off. And gravity is measured in kilograms. That's not what. Oh Lord. Oh sorry. I believe I forgot this. Meters per second squared. Alright? So there are two versions to the pendulum experiment and the graphs. And I'm going to show you both today. You notice in this one we plotted t on the y-axis and the square root of L on the x-axis. I'm going to show you a different way it can come in the exam. Alright, so let's do the pendulum experiment a different way now. Right? Remember, both ways can come in the exam, so it's really useful to know both. So once again, same formula. We make the string a certain length, we change the length of the strings, and then we try to time how long it takes to go back and forth. Alright, so I'm going to alter this formula a different way this time. I hope that you are familiar with the concept that whatever you do to one side of an equal sign in maths, you can do the same thing. You have to do the same thing to the other side. So what I'm going to do, since I'm allowed to do that, I am going to square everybody on this side. So I'm going to take the t and square it. But for it to remain mathematically the same, if I square this side, then I have to take the other side and also square it. It looks complicated, but it's going to be easy to simplify. T squared is just simply t squared. This squared belongs to everybody here. So that means this squared belongs to the 2. So the 2 needs to be squared. The pi needs to be squared. But when the squared comes in contact with the square root, when a square root and a squared meet, they cancel out. No, that's not the cancel out symbol. They cancel out, leaving you with just the L on G. So that's something to note, not only for physics, but it can help you in your maths exam as well. So let's work this out. Now, well, let's do this part easy here. You have the L on G, because I told you the square root and the squared will cancel out. Let's work this out. 2 squared, there's a secret multiply here, multiply by pi squared. You can try that on your calculator. I'm just going to put it here. 2 squared multiplied by pi squared. Remember, pi is just, we can round it off to 3.142. So let's work that out. 2 squared multiplied by 3.142 squared. And we will get roughly 39.5. If we round it off to 1 decimal place. So that means 2 squared multiplied by pi squared, we can replace it with 39.5. It's really useful to note in the exam. Sometimes the examiner does this step for you in the exam, right? And of course, you won't understand how we went from here to here, but now you do. But instead of putting 39.5, 39.5 is so close to 40, they may just put what instead? 40. And of course, before you didn't know how that 40 came up there. Now you know. So let's go with the 40. Right? I think that's, I've seen 39.5 in some exams already, but let's keep it at 40 to keep it simple. Right. So the examiner now tells you that you need to plot certain things on the graph. Something needs to go on the x-axis, and well, something needs to go on the y-axis. So, let's see what's going to go on here. Let's slide the G underneath on this side here. So the G comes on this side here. We slide the G underneath the 40. And he says that, hey, I want t squared, not t squared to go on the y-axis. And I want L, the length of the string. Now notice it's just L, doesn't have a square root or anything like in the previous example. He wants that to go on the x-axis. So L goes on the x-axis and t squared goes on your y-axis. So let's make 40 on G the subject. So there's a secret multiply here. So if we were to do this as so, the L is a multiply, throw it across, it becomes a divide. And we get 40 on G. Remember, T is going on our y, T squared, sorry, is going on our y-axis, and L is going on our x-axis. To calculate gradient, we need to take the y values and divide it by the x values, which is exactly what we have here. So there's no tricks. So that means when we find the gradient, it will be equal to 40 on G. So let's assume that we plot the graph, the t squared values against the L, we draw a best fit line, blah, blah, blah. The usual stuff. And let's say that when we got the gradient, we got 3.8 as our gradient. Right? So that means whatever we get as our gradient from this graph will be equal to 40 on G, and our gradient just happens to be 3.8. Let's calculate the value of gravity on Earth using these values. So let's use it here. I'm going to put this over here. 40 on G is equal to 3.8. Let's solve for G. 3.8 is the same thing as 3.8 on 1. Let's cross multiply. G multiplied by 3.8 is just 3.8 multiplied by G, and 40 multiplied by 1 is 40. Solve for G. 3.8 is a multiply, throw it across, you get a divide. Let's work that out. 40 divided by 3.8 is 10.5. So according to our experiment, gravity on Earth is 10.5. That's different from the actual value, which is, well, it's pretty close. Right? Keep in mind that when you do these experiments, you're going to make mistakes, and that's going to like alter your final value. So I hope you understand the difference between the labeling of the axes. In the last example, it was the square root of L and T. This time it's T squared and regular L. And don't forget about this value here, how we got the 40. Sometimes they're going to put 40 in the exam, sometimes 39.5. Just go with whatever the examiner tells you. Alright? And if he doesn't tell you, well, I would suggest you use the 39.5, as the 39.5 is more accurate than the 40. Alright, so I really hope that this video cleared up a lot of stuff involving the use of gradients in different types of questions. In my next video, I'm going to show you the basics in transposing formulas, which is really useful. You're going to find a lot of teachers, they have, when they're explaining physics, the maths part is what keeps back the progress of the class. Like the theory part, to me, is pretty easy. It's just when you reach the calculations now, half of the class might be good at algebra, the other half might not be good at algebra, and the whole class just slows down at that point. So don't forget to subscribe and to share, and look out for my next video. Take care, guys.